Iron is an essential trace element required for numerous biological processes, including oxygen transport, cellular respiration, DNA synthesis, and enzymatic reactions. Although iron is abundant in nature, iron deficiency is common due to the complexity of iron absorption, transport, utilization, storage, and regulation in the human body. Because excess free iron is toxic and there is no regulated pathway for iron excretion, total body iron balance depends almost entirely on tightly controlled intestinal absorption and efficient internal recycling. In adults, total body iron content averages 3 to 4 grams, varying with sex, age, body mass, and physiological state. Daily iron losses are small, about 1 to 2 milligrams per day, and occur primarily through desquamation of gastrointestinal epithelial cells, minor blood loss, sweat, and urine. These unavoidable losses must be matched by dietary absorption. Iron is distributed among several functional and storage compartments. Hemoglobin contains approximately 65 to 70% of total body iron, which is approximately 2.5 to 3 grams in a 70 kilograms adult. This pool is essential for oxygen delivery to tissues and carbon dioxide transport to the lungs. Myoglobin accounts for 5 to 10% of total iron, which is approximately 250 to 400 milligrams, and facilitates oxygen storage and diffusion in skeletal and cardiac muscle. Storage iron comprises 20 to 25% of total body iron, amounting to 800 to 1000 milligrams, mainly in the liver, spleen, and bone marrow. It is stored as ferritin and, when excessive, as hemosiderin. A small but critical fraction of iron is incorporated into iron-containing enzymes and proteins, including cytochromes, catalase, peroxidases, and iron-sulfur cluster proteins involved in mitochondrial oxidative phosphorylation and intermediary metabolism. Iron requirements vary with age, sex, and physiological conditions. Infants and young children have increased requirements due to rapid growth and expanding blood volume. Adolescents, especially females, require more iron due to growth and menstrual blood loss. Adult men require approximately 8 milligrams per day. Premenopausal women require approximately 18 milligrams per day, primarily because of menstruation. Pregnancy markedly increases iron requirements to about 27 milligrams per day, reflecting expansion of maternal red cell mass and fetal iron needs. Despite these requirements, only a small fraction of dietary iron is absorbed. The majority of iron needed for erythropoiesis is supplied through internal recycling mechanisms. Daily iron demand for erythropoiesis is approximately 20 milligrams, far exceeding the amount absorbed from the diet. This demand is met predominantly through the efficient recycling of iron from senescent red blood cells. Red blood cells have an average lifespan of 120 days. Aging erythrocytes are removed from circulation by macrophages of the monocyte macrophage system, particularly in the spleen, liver, and bone marrow. Macrophages phagocytose senescent red cells and degrade hemoglobin within lysosomes. During heme degradation, iron is released from the porphyrin ring by heme oxygenase. The liberated iron may be stored intracellularly as ferritin or exported into the circulation via ferroportin, the only known cellular iron exporter. Once in plasma, iron binds to transferrin, which transports it primarily to the bone marrow for reuse in hemoglobin synthesis. This recycling system conserves most body iron and is essential for the sustained erythropoiesis. Dietary iron exists in two distinct forms. Heme iron, found in animal products such as red meat, poultry, and fish, consists of iron bound within a porphyrin ring. It is absorbed intact and has high bioavailability. Non-heme iron, found in plant-based foods, fortified cereals, legumes, and grains, exists mainly as inorganic iron salts, predominantly in the ferric form. Its absorption is less efficient and strongly influenced by dietary factors. Iron absorption occurs primarily in the duodenum and proximal jejunum, where an acidic environment and specialized transport proteins facilitate uptake. Heme iron is absorbed intact across the apical membrane of enterocytes via heme transporter 1. Inside the enterocyte, Heme oxygenase cleaves the porphyrin ring, releasing ferrous iron. This iron enters the intracellular labile iron pool and may be stored as ferritin or exported across the basolateral membrane via ferroportin. Heme iron absorption is efficient and relatively unaffected by dietary inhibitors. Non-heme iron absorption is a multi-step process requiring chemical modification. In the intestinal lumen, non-heme iron exists primarily as ferric iron, which is poorly absorbed. Ferric iron is reduced to ferrous iron by duodenal cytochrome B, a ferroreductase located on the brush border of enterocytes. Ascorbic acid enhances this process by maintaining iron in the reduced state and forming soluble complexes. Ferrous iron is transported into enterocytes via divalent metal transporter 1. Within the enterocyte, iron is either stored as ferritin or directed toward export. Exported iron exits via ferroportin and is oxidized back to the ferric form by hephaestin, a copper-dependent ferroxidase. Ferric iron then binds to plasma transferrin. Several dietary components influence iron absorption. Enhancers include ascorbic acid, gastric acid, heme iron, organic acids such as citric, lactic, animal protein. Inhibitors of iron absorption include phytates in cereals and legumes, polyphenols and tannins found in tea or coffee, calcium, oxalates, aluminum-containing compounds such as antacids. Transport of iron involves transferrin, a glycoprotein synthesized in the liver that binds ferric iron with high affinity. Each transferrin molecule can bind 2 ferric ions, maintaining iron in a soluble, non-toxic form. Under normal conditions, transferrin is only partially saturated, providing a buffer against free iron toxicity. Cells acquire iron primarily through transferrin receptor 1 mediated endocytosis, especially in cells with high iron requirements, such as erythroid precursors. The transferrin iron complex binds to the receptor and is internalized into endosomes. Acidification of the endosome releases iron, which is reduced and transported into the cytoplasm, while transferrin and its receptor are recycled to the cell surface. In erythroid cells, iron is transported into mitochondria, where it is incorporated into protoporphyrin IX to form heme. Heme subsequently associates with globin chains synthesized in the cytoplasm to form hemoglobin. In other tissues, iron is used for the synthesis of iron-containing enzymes, cytochromes, and iron-sulfur proteins essential for mitochondrial respiration and metabolic pathways. Because iron cannot be actively excreted, systemic iron balance is regulated primarily at the level of absorption and distribution. Hepcidin is the principal hormone regulating systemic iron homeostasis. It is a small peptide synthesized by hepatocytes in response to body iron levels and inflammatory signals. Hepcidin binds to ferroportin, inducing its internalization and degradation. High hepcidin levels reduce ferroportin expression on enterocytes and macrophages, decreasing dietary iron absorption and iron release from stores. Low hepcidin levels allow ferroportin to remain active, promoting iron absorption and mobilization. Iron storage proteins are ferritin and hemosiderin. Ferritin is the primary intracellular iron storage protein. It consists of a hollow protein shell capable of storing thousands of iron atoms in a soluble, non-toxic form. Ferritin synthesis increases when intracellular iron is abundant and decreases when iron availability is low. Hemosiderin is an insoluble iron storage complex derived from partially degraded ferritin. It accumulates when iron stores are excessive and serves as a longer-term storage form, primarily within macrophages. At the cellular level, iron metabolism is regulated by iron regulatory proteins 1 and 2. These proteins bind to iron-responsive elements on messenger RNAs encoding iron-related proteins, such as ferritin and transferrin receptor. When intracellular iron is scarce, iron regulatory proteins bind to iron-responsive elements, increasing iron uptake and reducing storage. When iron is abundant, iron regulatory proteins dissociate, allowing increased ferritin synthesis and decreased transferrin receptor expression. In conclusion, Iron metabolism is a tightly coordinated physiological process involving absorption, transport, utilization, storage, and recycling. Distinct mechanisms govern heme and non-heme iron absorption, while systemic iron balance is maintained primarily through regulation by hepcidin, ferroportin, transferrin, ferritin, and iron regulatory proteins. These integrated mechanisms ensure adequate iron availability for essential biological functions while preventing iron excess and toxicity.